Quantum measurement. It's been quite a while since I've did that scoping, so I should have watched the video with my computers. I took the computer off, yeah, so that I can work on the desk. So let's look at the key points. Quantum superposition states that the particle exists in an infinite number of possible states until the moment of observation, at which point only one state comes into existence. This is called the Copenhagen interpretation of quantum mechanics. It's a very strange concept. I think I should adjust the EV. I'm going to leave it like that. It's a bit difficult to adjust it now. I have to stop the video. But this is a very strange concept. I mean, that's not how the normal world works. So I was wondering, is it just the theory that does that, or is it, do they really think that it's not in a determinate state until you observe it? I think that is what this quantum mechanical concept said. It's not in a definitive state, the quantum unit, until you observe it or measure it, and then it suddenly collapses into one of those states. Until the moment of observation, a particle can be in superposition of more than two states at once, which is called quantum superposition. So that one includes that one. Two particles can be in a single superimposed state. A measurement of the state of one particle immediately places the other particle in a definite state. Quantum entanglement. Bell's inequalities. Local realism is violated by quantum mechanics. Well, you first have to know what local realism is, because a photon or electron does not know whether to be a particle or a wave until the instant of measurement with the appropriate instrument, which irrevocably selects which state to manifest. So, particle or wave, it depends on how you measure it or how you observe it, what it encounters. It's almost like the thing doesn't exist until you observe it. That's the impression I'm getting. It's like it's in a ghost state until you observe it, and then suddenly it says, okay, something in the real world, I've encountered something in the real world, so now I become part of the real world. If you don't observe it, it's in another dimension, because normal objects don't behave that way. So it's like it's in another dimension, and when it encounters reality, but a physical object is just another quantum unit. Do the physical objects, when they interlace, they become real, and when they separate, they are in this multidimensional state or whatever. Local realism cannot be built in quantum mechanics using hidden variables to eliminate the need for information transfer to be faster and lighter, seemingly required in the delayed choice experiment. Local realism cannot... I think that's what this local realism is. It becomes real when it encounters physical objects, either observer or a measuring device. Okay, it's a short chapter, but man, that's a very weird one. Let's see if I can summarize it. Page 70. Quantum description of mass, the issue of measurement and observation. Observation changed the rock into something else. What? When you measure the intensity of measurement, quantum world, object, observed or measured. The object being observed or measured does not apparently have a definite physical state or set of properties before the action of measurement is completed. It's in this ghost state until it's observed or measured. Is everything still in view? Electron in an atom, quantum state, possible states, energy, the momentum that it could assume. It's wave functions, the sum of all the states or something. The complete wave function, individual quantum states, magnetic quantum number, angular, N for energy, L for angular momentum, a magnetic quantum number, M. The quantity A is a complex number, related to the probability of finding a particle in a particular state. Complex conjugate. I better write something. Okay. I think I might separate this, make this into two recordings. Measurement or observed. That pencil is too short. Measurement or observation. Observed and measured doesn't apparently have a definite physical state. Definite physical state. What's this? This is a HP. That's fine. I would like to make a note about this quantum numbers. In energy, L angular momentum, and M is the magnetic. Quantum superposition. That's again that it's the concept that it can be it's in a suspended state. It's all this all the states are present, and it only collapses upon observation. Copenhagen interpretation. Enough of 70. Let's do 71. Pause. I want some tea. Ooh, tough chapter. Since this is such a difficult chapter, I think one should I should keep looking back at what I've learned or gathered up to that stage. Otherwise, I'm going to get lost. Measurement, observation, and it collapsed into the state and the quantum numbers. Okay, not too serious. Deep theoretical issue since the 1930s. What? Another way to state this said initially particle superposition of many quantum states, but after observation the particle is found in a specific state of a probability. The full state contains far more information particle than what is found in any particular measured state. So where does all of this information go? Does it get destroyed? Irvin Schering proposed the thought experiment that dramatically describe the conundrum. I guess I want to make a note here. Superposition state, observation. What happens to all the other quantum information? The non-realized, realized quantum states. What happens to them? Schrödinger cat. Cat in a box. Two possible states, alive or dead. State vector. Probability. Conundrum. Even a macroscopic object in a quantum state of superposition for the indefinite length of time until you open the box. Schrödinger's cat. Superposition. Superposition state. Those are alive and dead until observation or whatever. So this again just superposition until observed or measured. 72. Tea break. If I can pause the thing, come on. Okay, it's running again. Eugene Wigner. This is not a familiar name to me. Proposed even more complicated experiment. The cat experiment. Whether the real world can be a mixed quantum state. What does that mean? That means it's not a ghost state or in another dimension, but it is real, and it's somehow all the states are present. It's a real thing. It's not It's part of the real world. Weakness friend. We can place the cat and the observation in an even more complex condition. Before the box is open, Wegener's friend is about to open the box, and Wegener himself is located some distance away but cannot see into the box. We now have three particles involved in the experiment: Wegener and Wegener's friend. When viewed by Wegener, Wegener's friend opens the box and immediately sees which state the cat's in, but Wegener does not. He sees Wegener's friend, who now knows the cat state, but Wegener now finds Wegener's friend in one of two states, either a state where the friend saw a live cat or a state where the friend saw a dead cat. For a long period of time, Wegener continues to see the cat. Wegener's friend is superposed quantum state, so a few days, weeks or years later, he finally asks his friend, was the cat dead or alive? Only when Wegener's friend finally tells Wegener the outcome does the state of the system collapse. But a portion of the quantum state had already collapsed for Wegener's friend after he observed the box. I'm going to summarize this. Observer A, observer B, cat is alive or cat is dead. Why did I make two arrows there? Why do I make it so small? Come on. He observes the cat in either a live or a dead state. He observes the cat, and this one might happen later. And now the reality is like it's in two parts, the cat. For A, it's still superposition, but for B, it is either alive or dead. And this is reality. So it's like there's almost a split reality. The reality is different for person B than it's for person A. There's a Wegener Schrödinger cat experiment. So what do we learn here? Page 72. He suggested that B looks at the moon, but A doesn't look at the moon. And then later A asks B, is the moon there? Is it out? So there's two realities. Something like that. 73. Tea break. The tea break gives me a little bit of time to chew on it. System in a definite state for Wegener's friend, or a quantum superior state for Wegener. Yes. Privileged observer. Quantum observation paradox. Two very different realities. What is this? Wegener's friend. Not share the same objective reality, which refutes the idea that there's a single physical world that we all experience the same way. So let's try and summarize that. Two different realities. Massimiliano Proetti, Edinburgh. Oh, that sounded Italian. Laser technology to reproduce weakness friend experiment by using photons that could one of two possible polarization states. So now it's a physical experiment that somebody went and did actually with photons. Polarization state. 6 photons in a state of superposition called quantum entanglement. So that one set of the three photons represented Wigner and the other set of the 3 represented Wigner's friend. Now I'm reading the whole page. When I started out of this process, I did another book where I choose only 3 words on a page. Now then your brain has to work very hard to make sense, extract information. Your brain has to really engage. And I thought I will summarize like that by extracting information. But this is step-by-step reasoning, and I don't think you can do it with this book. I don't think it will work. I'm not sure it will work. I think you have to read it really and think about it. Photons. Second set recorded polarization over while also recording the state of the first set. So it's 2 sets of photons, and it seems they are entangled. So now if you've got 6 photons, you've got 3 pairs of entanglement. Ignis friend. One set of the 3 photons represented Wigner, and the other set of 3 represented Wigner's friend. Set of 3. No, I'm not sure what's going on. 6 photons in a state of superposition. I mean, I think you entangle only 2. The result was that Wigner's set did indeed still record Wigner's friend set in a superimposed state, even though it had measured and recorded the state of the photons. Both realities can coexist at the same time, so the observation paradox is a real feature of the physical world. It leads to a variety of important considerations. It seems like what Wigner suggested is actually happening. That's the impression I'm getting from this, if I don't think and read about it at length. The second set recorded the polarization of a photon while also recording the state of the first set, and whether it was still in the superposition of the state of the photon. The result was that Wigner's set did indeed still record the result was that the Wigner set did indeed still record the Wigner's friend set in a superimposed state, even though it had measured and recorded the state of the photons. Both realities can coexist at the same time, so the observation paradox is a real feature of our physical world. So a little experiment with photons. How do you do a photon? I can't remember. No, I think something like that. 6 photons, entanglement. Entanglements. realities exist. I didn't know about this. This is a new one on me. And it seems it's real according to this experiment. Tea time. We have always believed that science is based upon a consistent background reality, about which all observers will agree. The weakness friend paradox says that under some situations there is no single underlying reality. It's a little bit information about Eugene Wigner, tannery, a scene position Kaiser Wilhelm Institute, X-ray crystallography, study quantum theory of Schrödinger, group theory, mathematical statement of symmetry, group theory and symmetry in atomic physics, published between 28 and 31, symmetry principles, permanent employment at Princeton University, 1937. When he became a natural U.S. citizen. Kaiser Wilhelm. Can't see where he originally was, and now he landed in America. Get the impression he comes from another country. Local realism. What is that again? Oh, I've forgotten. What's this? I understood it when I was working with the key points. I understood what local realism is. Local realism is violated by quantum mechanics because okay, that is the concept of particle or wave. It's both until it's observed. That's what local realism is: particle or wave. Observation, and then it collapses. It's either a particle or a wave. So that's what local realism is. Can behave either as a wave or a particle, but not both at the same time. How does a particle decide what to be? Quantum unit decide what to be. One experiment may be set up to measure the Broglie wavelength of an electron, while another set up to measure only its property as a particle, not as a wave. The classical experiment that reveals the lemma is the double slit experiment. Okay, what is happening here on 74? It's I don't want to call it a particle. Quantum unit experiment, particle or wave. Something about that. 75. Double slit experiment. Light diffraction interference pattern are observed. Electron. light were purely a particle, it would still produce a diffraction pattern, but would not interfere itself in the double slitting. Instead, it would again leave a simple diffraction pattern. What now? What now? What now? So electron and light, double slit experiment. Wheeler proposed the delayed choice experiment based on the ability of light waves to interfere with themselves in the double. A photon is emitted by a laser pass through two slits to produce a familiar interference pattern caused by the wave-like behavior of light. But one of the slits is blocked, so the photon acts as a particle and passes through the open slit to produce a bright point on the screen as a particle could. Okay, light interference pattern. If light were purely a particle, it would still produce a and then Archibald Wheeler delayed choice experiment. Light waves interfere with themselves. Photon is emitted by a laser. It's a familiar interference caused by the wavelength behavior. But one of the slits is blocked, so the photon acts as a particle and passes through the open slit to produce a bright point. Single photon. One slit blocked. Closed. So what is happening here? We've got the double slit experiment and we got a single photon, and it's now going only through one slit. 76. Well, my time was 1:02, so it's 12 minutes it seems. The photon knew at the time of correction that the slit was open or closed, so that it could register as a wave of particle on the screen. Reach the slit and then send information back. Of course, the travel time and speed of light for a nanosecond is considered this and could be transmitted quickly and still allow the phone to continue its smooth journey through the slit. So the reality is changed. Reality is changed, and what happens to the photon? Slit opens, second slit open, second slit closed. Professor Andrew Truscott, helium atoms, absolute zero. So it seems he might have done the experiment. Andrew Truscott, double slit experiment. But after the photon was sent through a laser beam splitter, a random what? Laser beam splitter. Beam splitter. A random number generator decided if it was to take a direct path to the detector or to interfere with itself and travel the longer path through the system. The result was that atom behaved as though it did not make up its mind. Atom, as though it did not make up its mind until the instant of detection at the screen, as whether it behaved as a wave or particle. Oh, what on earth is going on here? What it's saying, the atom behaved as though it did not make up its mind until the instant of detection at the screen as to whether it would behave as a wave or a particle. That is very weird. Good grief. The physical objects didn't change, didn't make the selection. It's just the actual detection right at the end. Similar kind of results have been obtained most recently when a satellite laser system was used to create two different paths for a particle or wave. Again, the photon behaved simultaneously as both until the moment when the detector end of the line framed the measurement one way or the other. In other words, it is the act of the measurement itself and the question the experiment asks that determines whether a particle behaves as a wave or a particle. This takes us to a related issue commonly framed as local realism. So what is it saying here? I get the impression that it's both particle plus wave until observed. Interaction with real world in between creation plus detection it's still up, it's still both. Undecided. Unless I read it in detail and think slowly about it, that is what I make of it. It's just, it's like writing it down. That makes it real. Otherwise, it's just up in your head and it's a thought. But putting it on paper makes it real. Can somebody say, there, you wrote it down? We've got it in black and white. Otherwise, it can say, I'm not sure, maybe he said it, maybe he didn't. Man, that's weird. Detection. Local realism. Then that thing comes up. States that a particle has specific property independent of the observer measuring it. Sir Isaac Newton and Einstein is what? So that there is an objective reality that exists independent of whether an observer is present or not. Localist states that the power has a specific property. Oh, independent of the observer measuring it. Oh, so it says something else. It's not what I thought. The concept of local realism has a specific property. That's what local realism says. Quantum mechanics says objects do not have a definable state until they are measured or observed. Okay. quantum mechanics. Observed.
They had a setup where a single photon is directed towards a double slit, and they can change the detection. What do they want to detect after it passed the slits? Do they want to see whether it interfered with the two slits, or do they want to measure which slit did it pass through? Now, what the measurements showed is that they measured both properties, both particle and wave properties. It is like the quantum state is the wave and particle property is like the two sides of a coin, and depending on what measurement you make, you if you want to look at the particle side of the coin, you're going to see the particle. If you want to look at the wave side of the coin, you're going to see the wave property. So it's complementary states of the quantum unit, or in this case, the photon.